Hello students, let us welcome to our second class in chemical equilibrium chapter. Till now I have explained what is equilibrium state, and we have also derived the relationship among various forms of equilibrium constant and how the value of equilibrium constant varies depending upon the mode of a reversible reaction, whether the original reversible reaction is multiplied by some factor or it is divisible by some factor n, and if the reversible reaction is reversed, what are the various forms of a new equilibrium constant in terms of original equilibrium constants. Okay, so today we will discuss very important topic that is also a very good long question from this equilibrium chapter. Okay, so before that you should know a term that is called reaction quotient. Reaction quotient and its relation with equilibrium. Its relation with equilibrium. Reaction quotient means it is the ratio of concentration of products to the reactants at any instant of time of a reversible chemical change. You know, in case of a reversible chemical change, reactants initially react to give you products, and simultaneously as soon as the products are formed, they also begin to react to give you reactants, and definitely there is a state of equilibrium achieved whenever some factors like concentration, temperature, pressure, all these remains constant. That is called equilibrium stage. But at any instant of time, if you take the ratio of concentration of product to the reactants, that is called reaction quotient. Okay, so you just write down its definition first. Reaction quotient is the ratio of concentration of products, or you can say if the reaction is in gaseous form, concentration of products or partial pressure of products to the reactants at any instant of time, of a reversible reaction, or it will be better you just write during the progress of a reversible reaction. Is that clear? So genuinely, if I consider an example of the type, for example, if I consider, let's say, AA hypothetical reversible change, BB giving rise to CC plus DD, and you are also familiar with this example. Okay, so if I write down the value of Q over here, reaction quotient, that will be equal to the concentration of product, C, concentration of products divided by concentration of reactants. You see, this is called the reaction quotient. Never get confused with the value of equilibrium constant. So equilibrium constant, K equilibrium, that is only applicable when at the state of equilibrium, at the stage of equilibrium. Okay, but except the equilibrium state, you can consider the ratio of products with reactant at any time, that is called reaction quotient. So at the state of equilibrium, you can compare this reaction quotient is equal to the equilibrium constant. So here in terms of concentration I have written, you can better write QC, that is equal to this much. Is that clear? For example, if I consider the formation of ammonia, you know, N2 plus 3H2, that is 2NH3. So if I need to write the QC for this equation, that will be product square N2 gas concentration H2 gas to the power 3. So this is the value of QC. So you just take the ratio of product to the reactant at any time, that is called reaction quotient. Clear? Let us explain now the characteristics of reaction quotient. Characteristics of reaction quotient. The value of Q varies. As you know, it represents the ratio between the concentration of product to the reactants at any instant of time during the progress of a reversible reaction. So its value varies from time to time. So I can write over here the value of Q varies in a reversible reaction as it depends upon the concentration or the partial pressures of reactants and products. Is that clear? Next, the value of Q, which represents the ratio between concentration of product to the reactant. If I can say the value of Q increases, that means the numerical portion increases. You see, Q, that is the concentration of products upon concentration of reactants. Is that clear? If the value of Q increases, what does it indicate? That means the amount or the concentration of products increases here. So the concentration of products is increasing, that means it clearly indicates that the reaction is proceeding in forward direction. That means the rate of forward reaction increases. I can write over here the increasing value of Q indicating that the rate of forward reaction is increasing. The increasing value of Q indicating that the rate of forward reaction is increasing. Clear? Next I can say, if the value of Q, the important characteristics, the value of Q represents the direction in which the reaction the reaction is proceeding. The reaction is proceeding. That is, if the value of Q is less than K, if the value of Q is less than K, that means Q is less than the equilibrium constant. So what does it represents? The reaction is moving towards forward direction. You see, the concentration of a product to the reactant is less than that of equilibrium concentration. So what does it indicates? That means the reaction proceeding in forward direction, because the concentration of product is less than that of a equilibrium concentration. That means a reaction is moving in forward direction, and it's vice versa. You can say if Q is greater than K, what does it indicates? The product concentration is more than that of a equilibrium concentration. So if product concentration is more than that of equilibrium concentration, then definitely the reaction proceed in backward direction. The reaction proceed in backward direction. Next, the last assumption you can say, if Q becomes equal to K, the reaction quotient becomes equal to the equilibrium constant, that means here the reaction is at, simply you can say the reaction is at equilibrium. The reaction is at equilibrium, that is, the rate of forward reaction is equal to the rate of backward reaction. So these are the important characteristics of reaction quotient. Clear? Next we will discuss the important long question, that is Lee-Chatelier's principle. Lee-Chatelier's principle. Statement, it states that when a system at equilibrium, is subjected to change in concentration, pressure, temperature, etc., then the equilibrium shifts in a direction in such a way that it tends to reduce, or you can say undo or minimize the effect of change. effect of change. Clear? That means in case of a reversible reaction in which the equilibrium already being attained, then if you disturb by changing any factor, measurable properties like concentration, temperature or pressure, then what does it state? That the equilibrium will adjust itself in such a way that to minimize that change. Suppose you increase the concentration or decrease the concentration, so the equilibrium has to adjust itself in such a way that it can minimize that effect of a change. Okay, so let's see first one, that is the change in concentration. How the equilibrium adjusts itself, you just see, that is change in concentration. Let us discuss. Change in concentration means, if a general equation I am writing over here, A plus B equilibrium C plus D. So these are reactants and these are products. So if you increase the concentration of any of the reactant, either A or B, if you increase the concentration of A only, then what happens? The equilibrium will shift in forward direction. So this is forward reaction, and this one is backward reaction. You see, in this case, if I increase the concentration of any of the reactant A or B, then what happens? The equilibrium, in order to minimize the effect of change, the increase in concentration, what happens? The reaction proceed in forward direction. That means the increase in reactant is utilized the formation of a product, so that the equilibrium remains unaffected. Is that clear? So in the same way, if you decrease the concentration of product, okay, if you decrease the concentration of either C or D, then what happens? Again, the reaction will proceed in forward direction, because as you have decreased the concentration of product, so the rate of forward direction will be more. The equilibrium is shifted towards forward direction as a result, and we can react with one another to minimize that decreasing or loss of a product from here. Is that clear? So I can write over here, with increase in, important point, with increase in the concentration of any reactant, the equilibrium shifts in forward direction. Clear? You can say that is the rate of forward reaction increases. Clear? Similarly, if you decrease the concentration of products also, the equilibrium proceed in forward direction. The rate of forward direction takes place to minimize that loss. Again I can write, with decrease the concentration of products, the equilibrium shifts in forward direction. Okay, and it's vice versa. Vice versa means, if you increase the concentration of products, then definitely to minimize that increase, the reaction will proceed in backward direction, so that the increase in product can be converted into reactant, so that the equilibrium remains unaffected. Is that clear? And it's vice versa. Simply I can write, and it's vice versa. Vice versa means, if you increase the concentration of a product, then the equilibrium shifted in backward direction. Backward direction. Equilibrium shifted in backward direction. If in other way I can say, if you increase, if you decrease the concentration of reactant. If you decrease the concentration of reactant, equilibrium shifted in backward direction also. Backward direction. That is the meaning of this vice versa, opposite. Very easy. So this is the effect of a concentration. If I consider the formation of ammonia, let's say the formation of ammonia. Let me vanish it first. For example, if I consider the formation of ammonia like this, N2 plus 3H2 gas giving rise to 2NH3 gas. Here we see, simply I can write, if we increase the concentration of a nitrogen or the concentration of a hydrogen, then tell me the equilibrium shifts towards forward direction, so that the yield of ammonia will be more. That is, the yield of ammonia will more. Again I can say, if the concentration of ammonia decreases, then to minimize this decrease, that effect of change, N2 and H2 react in forward direction again to balance the concentration of ammonia. So if concentration of ammonia decreases, then also equilibrium shifts towards forward direction. Okay, so this one is forward direction, this one is backward direction. And its opposite, if I consider, if the concentration of N2 is decreasing, or you can say the concentration of H2 is decreasing, then you can easily tell me equilibrium shifts towards backward direction. Again, if the concentration of ammonia also increases, then equilibrium shifts towards the backward direction to minimize or to undo the effect of increase or decrease in concentration. Clear? Now let us consider the effect of change of pressure on equilibrium. What will be the effect of pressure after concentration? Next important factor, that is effect of change of pressure. Effect of change in pressure. Just remember a statement over here. With increase in pressure, the equilibrium shifted from higher number of moles to lower number of moles in a gaseous reversible reaction. So with increase in pressure, the equilibrium always shifts from higher number of moles to lower number of moles. You see, if I consider N2, again the same example I am considering over here, giving rise to 2NH3. That clear? So this is forward reaction, and this one is backward reaction. Is that clear? So in reactant side, the number of moles, that is 1 plus 3, that is equal to 4, and here the number of moles, that is 2. If I increase the pressure, then the equilibrium shifts from higher number of moles to lower number of moles, that is towards the product side. More amount of ammonia will be obtained. So from higher number, from reactant side to product side, because here the number of mole is 4 and here in product side the number of mole is 2. So the equilibrium shifts in forward direction. Shifts in forward direction, that is towards the product side, towards the product side. So evaluation of ammonia increases, the production of ammonia increases. The production of ammonia increases. Clear? And it's vice versa. If you decrease the pressure, the equilibrium shifts in backward direction. Backward direction. That clear? So this is the change in pressure, the effect of pressure. So with increase in pressure, the equilibrium shifted from higher number of moles to lower number of moles. If the equation is reversed, let's say 2Na3 and 2 plus H2, then the similar case is there. You just focus with increase in pressure, the equilibrium shifted from higher number of moles to lower number of moles. Is that clear? And it's vice versa. Next we will discuss effect of change of temperature. Effect of change of temperature. So here we can consider the reversible reaction at equilibrium into two categories. One is exothermic and another one is endothermic. Okay, so you just remember again the first point. For an endothermic reaction, increase in temperature shifts the equilibrium in forward direction and it's vice versa. That means for endothermic reaction, if you decrease the temperature, the equilibrium shifts in backward direction. The second one, for an exothermic reaction, decrease in temperature shifts the equilibrium in backward direction and it's vice versa. That means if I consider a reaction, like again I am considering that one, N2 plus 3H2 giving rise to 2NH3 gas, and here the value of del H, that is minus 92.4 kilojoule per mole. Is that clear? So here you see, since del H is negative, the reaction is exothermic. Exothermic means energy is released during the formation of ammonia. This is forward reaction and this one is backward reaction. So since the reaction is exothermic, the product ammonia is obtained due to the evaluation of energy. This is exothermic reaction, heat energy is released. So definitely the system needs the temperature should be decreased. So decrease in temperature favors the formation of ammonia. Okay, so if you increase the temperature, then the reaction will occur in backward direction, decomposition of ammonia will take place. So very easy, you can remember. So for this reaction, since it is exothermic, with increase in temperature, okay, the equilibrium shifts in forward direction and more amount of ammonia is obtained. Clear? So sorry. So this is the equilibrium shifts in forward direction and more amount of ammonia is obtained as the reaction is exothermic. So definitely that is decrease in temperature, and it's vice versa. So vice versa means, you know, if temperature is increased in this case, then the equilibrium shifts in backward direction. Similarly for endothermic reaction, if I consider for an endothermic reaction, increase in temperature, because in endothermic process energy is absorbed. The system needs heat energy. That means you have to increase the temperature. For an endothermic reaction, increase in temperature shifts equilibrium in forward direction, and it's vice versa. Forward direction and it's vice versa. Is that clear? Okay. Next we'll see next case, that is if after explaining the change in concentration, pressure and temperature, then next one is effect of addition of inert gas. So inert gas means which do not interact with inert gas, do not interact with reactants and products. So they do not interact. That's why these are known as inert gases. Okay. So there are two cases at, let's say, constant volume. At constant volume means as they do not interact with the reactant molecules as well as product molecules. That means the number of moles remains same. The number of moles of reactant and products remain same, so that equilibrium is not affected. Okay. So in this case, at constant volume, the number of moles of reactants and products remain same, so that the equilibrium remains unaffected. There is no effect on the state of equilibrium at constant volume. But what about at constant pressure? At constant pressure, if I consider at constant pressure, so at constant pressure, the addition of inert gas results the increase in volume. Okay. So at constant pressure, the addition of inert gases results the increase in volume. So if the volume increases, then the number of moles also decreases. As a result, As a result, the number of moles decreases. So in order to minimize this decrease, the equilibrium shifts towards the more number of moles. That clear? So in that reaction, N2 plus 3H2 all are gases, equilibrium 2NH3 gas, let's say. So in this case, at constant volume, there is it can't affect equilibrium. The equilibrium remains unaffected. But what about at constant pressure? At constant pressure. So at constant pressure, you know, the volume increases. So if the volume increases, then the number of moles per unit volume decreases. The number of moles per unit volume decreases. So if the number of moles decreases, then the equilibrium will shift towards the more number of moles. So in this reaction, more number of moles, that is in this side. So the equilibrium shifted, the equilibrium will shift in backward direction. The equilibrium will shift in backward direction at constant pressure. Next, the final factor, that is effect of catalyst. Effect of catalyst. As I have told you earlier, that an catalyst does not affect the state of equilibrium. A catalyst does not affect the equilibrium. However, its presence brings the establishment of equilibrium earlier. Because the presence of positive catalyst increases the rate of forward reaction as well as the backward reaction. As a result, the establishment of equilibrium will be faster. Okay, so overall summary of Le-Chatelier's principle can be summarized as, just remember, I am doing it. Le-Chatelier's principle, that is first one, that is concentration. Okay, so if you increase the concentration of any reactant, okay, reactant product, so if you increase the concentration of any reactant, then, or increase in concentration of any reactant or decrease in concentration of product, then the equilibrium shift. Equilibrium I can write shifts in forward direction. If you decrease the concentration of reactant or you can increase the concentration of product, that only shifts the equilibrium in backward direction. So this is the effect of change in concentration. Next, pressure. Pressure. In case of a gaseous reversible reaction, simply write with increase in pressure, equilibrium shifts towards lesser number of moles, and it's vice versa. You can write with decrease in pressure, that is, and it's vice versa. You can write and it's vice versa. Clear? Next, temperature. If the reaction is exothermic, that is del H, that is negative, energy is released, then decrease in temperature shift the equilibrium in forward direction. Is that clear? So if the reaction is endothermic, del H, that is positive, so increase in temperature in forward direction, and there vice versa. Then effect of addition of inert gas. Addition of inert gas at constant volume, unaffected. Equilibrium remains unaffected. At constant pressure, the equilibrium shifts towards more number of moles, or you can say at constant pressure the volume increases and number of moles decreases, that is the equilibrium shift towards more number of moles. You can write. Next, catalyst, that is no effect, unaffected. Establishment of equilibrium will faster. So these are the basic summary of your Lee-Chatelain principle. Okay, so one of the important long question. Hopefully you guys got it. So thank you.